Okay, I think we're recording again. All right, so good morning, everyone. I decided I would try to do this in the morning when maybe I'm a little more energetic. We'll see how that goes. Um, Hope you're all doing well and hiding from the virus and whatnot. Okay, I checked over the quizzes that you all submitted. This sort of format seems to be working well for me. Hopefully, it's working well for you. Um, and it's giving me um, fairly uh, good feedback on how you are doing. Hopefully, I'll remember to insert a few more quiz questions this lecture. So last time we talked about uh, the forwarding logic for handling data hazards. Okay, so we know that we can, for many data hazards, especially ALU to ALU type data hazards, we can actually completely resolve that hazard by forwarding. And so we early in the semester or early in chapter 4 we talked about forwarding, but sort of from a theoretical standpoint. And then last lecture we looked at it. We kind of looked under the hood a little closer at it. And then of course in lab you're going to actually implement forwarding. So we're sort of progressively looking deeper and deeper into the topic. So real quickly, one of the quiz questions was identify the data hazards in this instruction stream, and I got varied results. What I was really looking for was this kind of diagram that I keep drawing, where we circle T1 in the first add because it's the producer. That the first add is the producer of T1 that the second add is consuming. So the way I would say that is that there's a data dependency between the first and second add, and it has to do with T1. The first add produces T1, the second add consumes the T1. And then the second add produces a T1 that is different than the first T1, and the third add actually consumes that. And so we identify that with a circle and an arrow. Okay, and anyway, and of course we know that this third add is going to produce a T1, and there may be some code down below that actually consumes that T1. So we would have a circle and then an arrow pointing to the next T1 that gets consumed. And then, of course, the first add, it has a T1 and T2, and so we know that there has to be instructions ahead of us in the instruction stream that actually consume that. Okay, so, well, that's all fine and dandy. But if you recall, when we were talking from a more theoretical standpoint, there really is a couple of data hazards or situations that forwarding is not enough, right? So when we have ALU to ALU type instructions, data dependencies, we can forward around the ALU. But when the data that we need is produced later in the pipeline, okay, for example, a load word produces the data that's needed in the memory stage. Well, then we have a data hazard that forwarding is not enough. Okay. So in order to resolve those hazards, we have to stall. Okay. Now I have a little terminology warning here because there's many different terms that I've heard this um, action being referred to as. Early MIPS documentation called it slipping the pipeline. And the reason they called it slipping is because you're actually holding the front end of the pipeline. So you're stalling the front end of the pipeline, but then you're letting the back end slip forward. Okay. Another way to visualize that is you're essentially holding the front end, and then you're placing no ops in the middle of the pipeline and letting the instructions that we're producing in the data hazard make forward progress. Okay. Now, so again, we can be pedantic and call it slipping, or we can just call it stalling, like the book refers to it as. You'll unfortunately probably hear me use the terms synonymously. You know, in my development research and development group, we refer to slipping, where you're resolving a data hazard by holding the front end of the pipeline and letting the back end of the pipeline move forward. And we refer to stalling, where we actually just hold the entire pipeline. And there are situations in the wild where we do either or. Okay. Okay. So let's look at our diagrams here real quickly, just to kind of understand what's going on. So we can see that um, that really the load word produces its value. In this case, okay, well let's first of all let's identify our data hazards. Well, this is actually the same instruction stream we looked at previously. Okay, let me go back to it here, and we have a bunch of stuff all written up here. But here's our data hazard, right? And so this is the one we're concerned about. We have an AND that's consuming register 2 immediately following the load word that's producing it. Okay, so as you recall last time, I said let's ignore that particular situation, and then we went on to look at the other data hazards that could be handled via forwarding. Well, today we're gonna talk about how to handle that data hazard between a load word and an immediately following instruction. Okay, so again, the load word produces T2 in the mem stage, which in this case is cycle 4. Okay, and the issue is that the AND, okay, is immediately following, and so it actually needs its value in cycle 4 at the beginning of cycle 4. Okay, when it's in the execute stage. So if we didn't slip the pipeline, we would be in this situation where the AND needs its data in the beginning of cycle 4, the consumer of this data hazard, and the load word would be producing its value at the end of cycle 4. So again, our pipeline isn't magical and is not able to go back in time. So we have to correct this issue in a way other than forwarding. And so as I have talked about previously, what we're going to do is we're going to hold these instructions, okay, these bottom instructions here. We're going to go ahead and hold them in the pipeline and not let them move forward, and then we're going to let the load word move forward. So what that's going to do is that's going to automatically insert no op. So let's go ahead and look at a single cycle diagram, and it's a little easier sometimes to see how this is depicted with a different diagram. So where we actually perform the slipping is actually when the consumer instruction is in the decode. Okay, so in that case, we're going to have the AND here, and we're going to have the load word is going to be just immediately following. And let's see what else. Well, we don't. Let's see. Oh, the or is the instruction here. Okay, we don't actually have enough information to know what's in the mem stage at this time. Okay, relating it back, this is actually this is cycle 3. Okay, so clock cycle 3. If we look at this is our multi-cycle diagram, we can see that in clock cycle 3, the load word, clock cycle 3 right here. Okay, the load word is in the ALU stage. The AND is in the decode stage. And, well, this is confusing because this diagram has already added a slip here. But anyway, when we haven't added the slip, then we have this diagram. So, okay. Now, what we want to do basically is we want to freeze this part of the pipeline, okay, and then let this part of the pipeline go forward. Okay, so then in cycle 4, what we're actually going to see. Okay, so I'm going to change this to cycle 4. We're going to see that the load word has now progressed, okay, to the mem stage, and then you can draw a bubble or a no op, whatever you want, okay, in that particular cycle. Okay, so what we've done is we've held the front end of the pipeline and we've let the back end go forward. Okay, so that's the scenario we actually see here. Okay, okay, the all right, so these little multi-cycle diagrams that they draw with the cutesy diagrams and pictures can oftentimes get confusing. Um, but let's make ourselves some room here. I'll show you what the well, yeah, I'll just go ahead and erase all this. I'll just go ahead and show you what the multi-cycle diagram would look like if you were doing this at home. Okay, so um, okay, so we have the load word, we have the and then we have an or that follows, and so the load word is going to be if, okay, id, ex, mem, right back, okay, and then the okay, we'll fetch, and then we'll decode, and then and then of course the or will fetch, okay. Draw that down. It's a lot easier to do this on graph paper. Then what will happen is I like to just go ahead and show the and being in the decode. Let's see. So this is if we look at cycles, this is cycle 2, 3, 4. So what we see is that if we slip the pipeline, then the and actually hangs out in the decode for an additional cycle. So in cycle 4, we see that the and is actually still in the decode, whereas notice the load word is making forward progress. Okay. Now, because the and is stuck in the decode, well, the or was fetched in cycle 3. Well, we have to stall the front end of the pipeline. We can't just let things go out of order right now. This is an in order pipeline. If you take my 538 advanced architecture class, we talk about how to actually run instructions out of order. Whoops, what am I doing here? Whoops, 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 whoops. This is in cycle 4, the or remains in the fetch stage. Okay, so because again, the front end of the pipeline is held constant, and the back end of the pipeline is allowed to make forward progress. So that's how we resolve data hazards when forwarding is not enough. Now, in our simple pipeline, that exists when you have a load word followed by an instruction that immediately consumes the value the load word is producing. Okay. Uh, so I've talked about this. A slip is when we stall the front end of the pipeline, allowing the back end to make progress. Okay, that has the effect of inserting instructions between our data dependent instructions. Okay, so that resolves our data dependency. Now, what's interesting is if we go back and look at this diagram, we're still actually going to rely on forwarding. Okay, so to resolve this particular hazard, okay, between the load word and the and, we actually need forwarding, we need stalling in it or slipping in addition to forwarding. Because what'll happen is, so we allow one one cycle of slippage here, which is what we see here, okay, and so the and still needs its value when it reaches the execute stage, okay? And if we go back to this diagram, well, let me pencil that in right here. We see that in cycle 5, okay, the and is going to reach the execute stage, and we see that in this diagram as well. So that's good. There's some consistency here. So we still need to forward, and that's what's going on right here. Okay, we can see that right here. In cycle 5, the load word, the value of the load word, we've pulled it from memory in cycle 4, and then it's now actually residing in this pipeline register, which, if you remember our convention, this is called the mem write back pipeline register. So the data that the load word is producing, which is coming from the memory read, is actually residing in that mem write back pipeline register. So we basically have to pull it from there and forward it to our ALU. So if you recall, when we talk about our forwarding paths in our processor, okay, let me show you. Let me go ahead and redraw our processor, and I'll show you Okay, I still haven't found that almighty clear button that will clear a page, so probably need to spend a little bit of time. My poor little M-Core tablet is doing all that it can to keep up. Okay, so let's go ahead and draw. We're mainly concerned about the back end of the pipeline in this case. So we have our ALU. It's going to have these muxes, and again we're going to combine. We're going to have a 4-input mux now. Okay. Let me go back and look and see here. It's right here, so it's the RS one. So it'll be this mux here. Okay. All right. Let's see here. Man, I need to adjust the size of that eraser. Okay. And then this goes into the, whoops, that's a really bad looking register, but we'll run with it. It's a little different writing on a screen than it is on a whiteboard, but I feel like I'm getting maybe a little bit better. I don't know. Okay, and then here's our data memory, and then of course, here's our, this is our mem write back register. Okay, I'll just call this mem. And so the data is actually here. Now, if you recall, there in our pipeline, when we looked at the diagram before, there's actually a mux in this stage because the ALU result goes here. Okay, so this is your ALU output, goes into the address port of your memory, but then it also goes around here. Okay, and because we use the path through memory for a load word, but then for pretty much all the other ALU instructions, we forward around the ALU. Anyway, so we have this path, and this, if you recall, is going all the way to the decode stage back to where the register file is. Okay, well, the forwarding path that we're going to use is we just pick this off, right? And last time I showed you how to actually create logic that sets the select line on that 4-input mux, and of course you're going to do that in lab. Okay. Okay. So just to recall, that's how you're going to do that forwarding. Okay. So well, the question is how do we actually perform this slip? Okay. So for one thing, how do we stop the front end of the pipeline from making forward progress? Okay. Well, so we need to add control signals to our pipeline registers. I don't have a diagram here that shows. Oh, here we go. This might work. Okay. Well, so this is our decode stage. Well, no, see, this isn't quite what I'm looking for. Do I have a blank page? Oh, well, here, we actually have a diagram here that Hennessy and Patterson provided us, so let's use that. Okay, so what we want to do is we want to hold this end of the pipeline and allow this end to go forward. Okay, so we need control signals on our pipeline registers. So for one thing, what we need is an enable. Okay, so if we have an enable on each of these registers. Now, interestingly enough, the program counter is almost like a pipeline register. It's really, the program counter marks the beginning of our pipeline. Okay, so we have an enable on these two registers in the front of the pipeline, and really what we do is when they're 1, then they go ahead and latch a new value. When the enables are 0 or deasserted, then they actually just hold the value they had before. Okay, so that has the effect, okay, of basically holding the prior instructions. And if you remember, I'll just go ahead and draw them up here. We had the and we had the or, and then we had the load word. Okay. Okay. Now, basically what we do is now we could add these enables on these other registers as well, like the IDEX and all that. And if your pipeline needed to support full on stalling, where we stall the whole pipeline, then you would also have enables on those particular pipeline registers. Okay, so I'll just draw them in here. Okay, and so what you would do to slip the pipeline, okay, is you would set the enables on your forward or front end registers to 0, and then you keep your back end registers set to 1. Okay, and so what that would do is that would then cause a break here, and the load word would move forward. The load word, okay, the load word would move forward because the value of the load word on the next cycle would then latch into this register, and then on the next cycle it would latch into this register. Okay, whereas your or that's in the fetch stage, okay, here would remain here because the enable is 0, which means that it's just going to hold the value that it had before, which was the address to the OR. Okay, and likewise the AND would stay where it's at in the decode stage here. Okay, because um, because the instruction that represents this AND here would remain in the IF ID register. Okay, and then now the question is, well, what do we do? What do we do with this part here? Notice I say, yeah, you need to, the enable needs to be asserted on that. On the next cycle, what do we want to be in the execute stage? And boy, this diagram really looks like crap after I've marked it up quite a bit. Okay. Um, so that's the question here on this slide. So okay, let's see. So to do so, we must add control logic to detect the hazard. Oh yeah. Well, I left out a very important part. We have to actually have a control logic to detect that hazard, and then we need to add control signals that I just showed you to the PC and the IFID registers. I'll show you a little bit later on what the detection logic looks like. Okay. But what else do we need to do? Well, when we hold the instruction in decode, something still has to propagate forward to fill in that gap. Okay, because what we're doing is we're creating a gap when we hold the front end of the pipeline and then we let the forward end go. You can imagine we're creating a gap in the pipeline. Well, and what I've shown you in all the little diagrams is we insert a no-op. Well, so the question is, how do we do that? Okay. And the answer is fairly simple. We do so by by zeroing out the control signals that change the state of the processor. Okay, so because really we don't care whether the data part of the AND moves forward. Okay, yeah, maybe it wastes a little bit of energy with the data part moving forward, moving data through the pipeline. But if we can actually flip the control signals, specifically the mem write and reg write, which are the control signals. You know what? I apologize. I keep getting this. No, I think this is right. Last time I listened to my lecture and it was very painful when I was getting all mixed up between reg write and write reg, and it's evident that the next time I provide this lecture, I need to clarify and not use Hennessy and Patterson's confusing ass terminology. It's kind of the advantage of recording the lectures. Before when I wouldn't record, I would fumble with it in lecture, and then my day goes on and I forget about it until next semester comes around and I fumble again. Whereas when I'm recording them and I go back and look at the recording, I'm like, oh my gosh, I didn't realize how bad I was fumbling on that. And it also, if I'm fumbling on it, well then it's obviously, if it's I understand this stuff very well. I do it on a daily basis. Then it must be really confusing for you. So next year, the students will hopefully benefit from me trying to somewhat untangle that confusing terminology. Really, this reg write should be called a reg write enable. That's what the signal should be called, and then that completely divorces it from write reg. It's a little less confusing. Okay. All right, that's a little bit of a tangent. Let's hold back to. Oh my gosh, this is beautiful. So okay, let's erase some of this mess so we can see what's actually going on. The little M core is just really struggling here. Okay, it's doing the best it can. Okay, so what we're doing is again we're holding the front end of the pipeline. And then the question is on the next cycle, Okay, on the next cycle, we of course said that the load word is going to bounce on over to here. But then the question is what's actually filled in on here? Well, it turns out we don't actually care about the data portion, which is all of this part here. Data portion, the way we've divided this diagram up, the data portion is the lower part, and then the control signals are the higher part here of our pipeline registers. Okay, so that makes it pretty easy. So we don't actually care what goes on the data part, as long as the control signals, and specifically the ones that control the storing of state, which would be the write enable for the memory and the write enable for the registers file, as long as those are zeroed out, then this AND appears to be a no-op. Okay, so you could look at it as kind of a neutered AND or something. You know, the data is still there, but the control signals to actually do anything are invalidated. So then, yeah, the data flows through the pipeline. You know, it gets replicated as time goes on, but the AND itself can't do anything. So here we have a mux we see, and what that mux is doing is it's allowing the control signals to come from the decode unit here, or it's putting in zeros. Okay, so what it's going to do is it's going to zero this out. Okay, so then on the next cycle, let's look at what happens on the next cycle. So really, to resolve this hazard, we only need actually one slip. Okay, we only need one cycle of slip. So on the next cycle, what's going to happen is our logic is going to determine that we've resolved the hazard. So it's going to allow the front end of the pipeline to then begin making forward progress. Okay, so we're going to, and of course the back end is going to continue moving. Okay, so what will happen is the load word will then progress to the write back, and then what's going to go in here? Well, it's going to be that kind of neutered AND. Okay, so the AND, which is a no-op because all the signals are zeroed out, and then at that point, we're going to allow forward progress of the actual AND, and so then we'll have the AND here, and then of course whatever. I don't remember what came after. Let's go look and see. An add. Okay, so let's go back. So we're gonna have our OR here, and then we're gonna have an add here. Okay, so and then again, then in this cycle, in the mem stage, is going to be essentially a no-op. Okay, it's going to be the data portion of the add, or the AND rather, but with the control signals zeroed out. Okay, so again, just for review, we do so by zeroing out the control signals, and we do so right here in the decode stage, and so you can actually accomplish this with flip-flops. Usually have a synchronous clear signal, and it's essentially a mux where it's muxing in zero kind of way of looking at it. And so you would essentially assert the synchronous clear for that one slip cycle. Now this all works very well for a 5-stage pipeline, but as we start talking about deeper pipelines, for example, the R4000 actually has requires 2 slip cycles. Okay, so if you dig through the MIPS terminology, they call that 2 load delays, whereas the 5-stage has only a single load delay. Okay, and so what that means is the load delay means there has to be a delay, 1 cycle delay between the load word and the instruction consuming the value that the load word is producing. And so for an R4000, the 8-stage pipeline, we would actually have to do this twice. So we would hold the front end of the pipeline still for 2 cycles and allow the back end of the pipeline to make 2 cycles of forward progress, and we would insert 2 no-ops into the pipeline. Okay, but again, for the 5-stage, so again, for the 5-stage, we only need the 1 cycle. For the 8-stage, we need 2, and that's where I was talking about pipelining has adds additional overhead. Each of those slip cycles that we have to add erodes away that ideal CPI of 1, which is why an 8-stage pipeline has a harder time achieving a lower CPI than a 5-stage. Or, of course, taking that to the extreme, a single stage, okay, the single cycle that you're building can very easily achieve the CPI of 1. But as we move to more aggressive processors, deeper pipelines, it becomes harder. Okay. All right. So the previous diagram showed a mux that would propagate zeros for mem write and reg write, which are the write enables for the memory and the register file. In actuality, that's accomplished with a synchronous clear that is built into the flip-flop. And again, just to reiterate, the mechanism to hold the front end of the pipeline and allow the back end of pipe is done with the enable signal on the flip-flop. So what I'm telling you is that with the signals built into standard flip-flops, we can actually, that's all the control signals we need to slip and whatnot, and stall the pipeline. Real quick, if we wanted to stall this pipeline, okay, which happens when you have data hazards, well, I don't want to confuse you too much, but there are situations when you would have to stall the entire pipeline, and a lot of time it has to do with, once we start talking about chapter 5 and we talk about memory hierarchy, where I'm saying, oh, this data memory is actually a data cache, and at times it has to stall the pipeline to refill data, and we'll talk about that in great length when we cover chapter 5 material. Well, so that would be a situation in which we have to stall the entire pipeline, and what we would do there is we would just set all of these signals to 0. Okay. Now, theoretically, we could actually slip the pipeline here and just hold the fetch, decode, execute, and mem stage and allow the write back to happen. Okay, that requires a bit more logic to orchestrate, and in the end, does it really provide that much of a performance benefit? Maybe, maybe not. For deeper pipelines, maybe. For little 5-stage pipelines, probably not. Okay. All right. So, okay, well, the fan out of this clear signal could get pretty large, and for the VLSI folks in the class, you probably have studied fan out and whatnot and know its effects. But it's essentially when you have a single signal that controls many logic gates or state elements, okay, which in this case would be state elements, and so what happens is that signal has a lot of capacitance to drive, which means that it adds significant delay, because now you've got a lot more capacitance to essentially drive. And let me see, I do have a whiteboard here, so let me just talk about fan out here. So remember that our registers are built with these flip-flops, and this is my pathetic attempt of drawing a flip-flop. Okay, and I'm saying, okay, you know, we're going to have this synchronous clear signal up here, and then what it means is we're going to have to drive it. Oops, we had a manufacturing defect there with the clear signal being broken. So now we're going to have to drive, in this case we're driving 3 flip-flops, but if you can imagine, you know, we might have to drive a whole lot more. And then, of course, if we're talking about the enables, right, so let's say this is our, well, let's put the enable here. If we have the enable, then we've got, you know, we've got another signal that's driving 3 flip-flops. And then, you know, remember I talked about approximately how many flip-flops. We said, well, there's 32 flip-flops here for this register. This one, you know, is like 96, and then, you know, so you're talking about, it quickly escalates when you're talking about the entire pipeline. This load quickly becomes hundreds of flip-flops. Okay, so you're talking hundreds of flip-flops. Now you have to drive hundreds of flip-flops with this single signal, right? So of course I wish I could just slide all this over. I probably could. I need to actually learn how to use this tool a little bit better. But um, so you're I'll just draw it over here. You're you're trying to drive this large signal. So what you're going to have to do is you're going to have to add a big buffer here. Okay, so you're going to have to take this signal and buffer it. And this buffer is going to have to be very large to drive all of these hundreds of flip-flops. Okay, so that's what I'm referring to as fan out. Well, that time, as you add a larger buffer and you've got more of these loads to drive, that increases the amount of time that it actually takes for this signal to propagate throughout the entire pipeline. So at some point that becomes very prohibitive and it becomes a critical path. Okay, so then we look for alternatives to actually simple alternatives to accomplish this same thing, this actual clearing and invalidation of the pipeline. Okay, I'm going to erase this mess here. And so again, Hennessy and Patterson talk about the very theoretical way to do this. Okay, I think we're rolling again. So there's going to be a slight break in the slides. Again, I'm getting used to learning this tool. I got a call from the roofing contractor that I needed to take. Uh, they're fighting with the insurance company trying to figure out whether my sheathing is up to code, but anyway, don't worry about that. So I don't know how seamless this connection is going to be. I'm still learning this tool, but anyway, let's pick up where we left off. We were at the 36 minute mark, so that's almost exactly halfway. So anyway, we have about another 40 or so minutes of lecture remaining. So okay, so where we left off is I was talking about the fan out. So the issue with this is with this approach where you have the a signal that clears the registers, the control registers, to turn instructions into a no-op, um, can create a large amount of fan out. So one way to combat that is to actually in your pipeline, okay, you have the pipeline registers. Part of that signal that flows from one register to the next. I'm going to draw, let's just pretend this is just a 1-bit signal, and it flows down your decode, execute, mem, write back. Okay. Part of that signal is an instruction invalid. Okay, so it's just an invalid signal. Okay. And along the way, you have a way of setting that. So that's how you would flush an instruction, which we're going to talk about control hazards in the next couple slides, and how we actually resolve them, the mechanisms to do that. And so you would use this invalid signal then to also flush an instruction. And then what happens is when you get to the mem stage, okay, and it looks at the mem write enable signal, okay, then it would also look at the invalidate signal. And if invalidate is asserted, okay, then that says, hey, this instruction has been invalidated and is essentially flushed. Okay, so it would not perform the write. Okay, and same thing when you have this loop back, right, to the decode stage, right? You have your register file, and it would look at the write enable for the register file being asserted, but then it would also look at this invalidate signal and say, hey, if that's asserted, it said, hey, this instruction was invalidated, so I'm not going to allow a write. Okay. And the same would go for the logic inside the execute that redirects the program counter. Okay, if it's a branch, then it's been invalidated, we don't actually want it to do anything. Okay, so again, that's how we can how we can do this. Okay. I'm trying to think here because branch is a little unique, and I'm trying to think of how that all plays in. If you invalidate a branch, yeah. Anyway, I don't want to add more confusion. I'll think about that at my own time and maybe get back to you on how branch is affected by that invalidate signal. Okay, so we talked about the mechanism that actually allows the slip. So in combination between holding the front end of the pipeline, letting the rear end of the pipeline go, and then invalidating essentially the instruction that would then uh, propagate out of the D code while you're holding the front end of the pipeline. So you invalidate, you insert a no op, you set the control signals to 0. All of these things mean the same thing. So now the question is, well, how do you actually detect this hazard? And if you recall when we talked about this earlier, we said that the detection of the actual hazard happens in the decode stage. Okay. Okay, there we go. I expand us up to full screen here. So in the decode stage, we actually then detect whether a hazard condition exists such that we have to slip the pipeline. And if you think about it, we have enough information, right? And it would happen when the AND was in the decode stage. So what we would do is when the AND is in the decode stage, we essentially look ahead of us in the pipeline to see if there is a load word that is supposed to be producing the value that we need. Now, because we only need one cycle between our load word and our consuming instruction, which in this case is the AND, then that actually means that we really only have to look one stage ahead of us. We don't need to look at the stage 2 stages ahead because if there's a load word 2 stages ahead of us, that's fine. That's producing a value that we need. That's fine because we have enough space. We just need to look at the instruction immediately ahead of us, and that's what this block of code does. Now, of course, I don't want to give it all to you because you're going to be describing this logic in lab. So of course there's something missing, and we'll talk about that. But essentially, what we're going to do is we're going to look and see at the instruction ahead of us, immediately ahead of us in our pipeline stage. So remember, the AND is in the decode stage, and we're detecting whether a load word is ahead of us in the pipeline stage. So how do we know it's a load word? Well, we know it's a load word if the mem read enable signal is asserted. Okay. Oh, real quick, talking about that signal, that we also want to invalidate that signal or zero that signal out when we flush an instruction. And even though it's a read enable, you might think, oh, well, that's a read enable. That doesn't have any negative effects. Once we get to chapter 5, you're going to see that just reading from the data memory, which is actually a data cache, can have a number of consequences. So we also want to zero out the read enable if we're invalidating a signal. And of course in lecture we just and in lab I have you just zero out all the control signals, and then you're hitting all the ones that need to be invalidated. And of course if you're in real life, if you're doing this, you would have an invalidate signal. And so you would also gate um, data cache reads with the invalidate signal. Okay. So again, if we look ahead of us in the pipeline, then we know that if the mem read is asserted, then we know that that we do in fact have a load word. Okay. So the next thing we have to do is check to see whether there's a valid hazard or data dependency between that load word and the instruction currently being decoded. So just like we did with our fetch logic, we look at the in this case we look at the RT signal of the instruction ahead of us, because the RT indicates the destination register that's going to be stored, and we check to see if it's 0. If it's 0, again we actually have a we actually don't have a data dependency because, and of course, why would you create a load word that writes to 0? I don't know, but we don't. If we do encounter that condition, we don't want to falsely stall. And this is where a computer architect may make an informed decision. One of the mantras that we talked about very early on in the semester was make the common fast. And so if you really want to make the logic simple, you might actually leave this 0 condition out because you're like, well, in this case, you're stalling. And so the only negative effects it has, or slipping really, the only negative effects it has is adding a 1-cycle delay. And so you may say, well, very rarely will we ever write to the, have a load word that's writing to the 0 register. So maybe in that case, we'll just, to simplify the logic, we'll not even detect this 0 condition. So do note that this 0 condition is optional. Now, in lab, I think I want you to put it in there, and in lab, timing is everything. You're not only am I checking correctness, but I'm checking timing on your pipeline. So you'll want to include that 0 check in your lab as well. Okay. The next thing we have to do is we have to look at both the RS and RT field of the instruction in decode, which remember is the and we want to see if it matches with the RT field of the instruction ahead of us. Okay, so if so far we've determined that the instruction ahead of us is a load word, we've determined that it's not writing to the 0 register, and now what we're going to do is we're going to check to see if there's a match between the source registers of our instruction in decode and the destination register of the load word ahead of us. Okay, and that's of course done with these two, and of course you can see that for the first the first two conditions are ANDed with the OR of this check, because you can have a data dependency either between the RS or the RT or both. I mean, you could have an instruction that's taking the value that the load word is producing in as both operands. Okay. Well, either operand, if there is a condition, you need to stall for. So anyway, this logic is important. So the result is, if you detect that, then you slip the pipeline. Now, what is missing? Okay. Well, this logic is assuming that the current instruction is using both operands, RS and RT. But now, if you recall, that's not always the case. And so we know, if we look at the use champ, we know whether the RS field is being used on the current instruction. So if we look at the use champ field, or the use champ signal from the decoder of the current instruction, then we know if use champ is asserted, okay, then we know that we're not actually using RS, right? We're not using that register because we're using the champ field. And similarly, if we look at the use immediate, okay, then that will tell us whether we're using RT. If use immediate is asserted, then that means that we are in fact not using RT, which means there is no dependency. If we're not using RS and we have a match between RS in the current instruction and RT in the instruction ahead of us, which we determined as a load word based on the prior conditions, well, if we're not using RS, then even if those two match, we don't have a hazard. Okay, and you go through this mentally when I ask you to identify the data hazards in the given instruction stream. Okay, we're just trying to figure out how, based on the control signals that we have available to us in the pipeline, how do we then detect that? Okay, and so again, the same thing goes for the RT field. So anyway, you have to add in the logic to account for the use champ and use immediate. And if you are using the let's say the immediate field, and there happens to be a match between the two RT fields, the worst case is if you don't have that condition, you would unnecessarily slip, interestingly enough, so it would just affect performance but not correctness. Now, for your lab, I'm checking for cycles to completion, so I care about that. So if your hazard detection logic is not working properly, then then points will be deducted. Anyway, okay, all right. And again, that's to prevent unnecessary slips of the pipeline. Okay, so we showed how to handle our data structural hazards. Oh yeah, going way back, we've showed how to handle structural hazards, which, if you remember, one of the major structural hazards that we resolve is the fact that we actually access memory in the fetch stage. We're actually reading instructions, and in the data memory stage, we're reading memory. We're from the data side. And the way we resolve that hazard is by duplicating the memories. Okay, that is referred to as a Harvard architecture. Okay, I don't know if I've talked about Harvard versus von Neumann, but when you have, in fact, let me grab a sheet of. Let me just grab this one. I may need it later on, so I'll have to erase it. But when you have a processor and you have separate memory. Okay, so this is instruction memory, and this is data memory. Okay. When you have separate memories for instruction and data, this is called a Harvard architecture. Okay. And of course, this was back in the day. I would assume that this concept was developed at Harvard, and so when in the early days of computing, they were kind of trying to figure out what's the right thing to do. So there were two competing architectures, and then the other one is a von Neumann, proposed by von Neumann. Okay, I think John von Neumann. Anyway, so when you combine them, okay, into, and I'm going to put instruction data. Okay, this is a, oh gosh, I'm not going to try to spell von Neumann in front of you all. There's some silent character letters and whatnot. Spelling has never been my forte. As a grown-ass man, I struggle with it all the damn time. As engineers, you probably all can empathize with me. Okay, so we have the Harvard architecture, and then we have the von Neumann architecture. And the Harvard architecture stores instructions and data in separate memories. The von Neumann architecture stores instructions and data in the same memory. And this is a perfect spot for a quiz. So I want you to define a Harvard architecture and a von Neumann architecture. Okay? And when we get to chapter 5, I'm going to show how we actually create what's called a modified Harvard architecture. And so, because what we'd like is for the programmer to have a view of memory as though it's a von Neumann architecture, but then under the hood, we want this Harvard architecture to resolve structural hazards. Okay, let me look for another quiz question here, because I realize I'm not giving quite enough quiz questions. I keep forgetting about giving quizzes. Kind of like when I'm looking out to the audience for feedback, I need to just think, oh, this would be a good point for a quiz question. Okay. All right, quiz question. In our hazard detection logic here, how exactly do we account for instructions that do not use the RS and RT field? Okay, so you may have to back up a little bit in lecture to remember that. So that's your second quiz question. Okay. All right, that'll be a good one. All right, so where were we? Alrighty then. So, okay, so we talked about structural hazards. Now, then we talked about data hazards. We just finished that. And again, I showed you the mechanisms to do data forwarding, and we want to do data forwarding when we can. But when we cannot do data forwarding, okay, then then we slip the pipeline, right? So, and I showed you the mechanisms to actually carry that pipeline slip out. Well, now the next progression is onto control hazards. Okay, so how do we go about resolving control hazards? Okay, hold on. I checked the time and it claimed that we've. Okay, I'm totally messed up on my time. I thought I was almost out of time. Okay, so we still have about 20 minutes here. Okay, good. So, we talked about control hazards previously from a theoretical standpoint. We're going to look a little bit further under the hood to understand how we actually resolve those. Just to recap, if you recall, there's the assume not taken is the easiest from the hardware standpoint. So we need a mechanism to flush instructions. Okay, so we talked a little bit about that previously. So the question is how to flush properly. How do we flush our instructions in our pipeline? Well, it's actually very similar, or it's basically the same thing to inserting no ops. We need to clear those control signals. So we pick the instruction that we're flushing, and I'll remind us what instruction that will be in a second here, and then we go ahead and we flush those instructions. Okay, we clear those control signals for that particular instruction. That essentially flushes that instruction. It invalidates it. If you're propagating an invalid signal, you would simply set that invalid signal for the instruction in that stage. Okay, so again, propagating the invalid signal actually makes things a lot easier. Okay, all right, so I knew I was going to have to use this again, so I'm going to go ahead and erase it. Someday I'll take the time to figure out how to do this quickly. All right. Okay. Oops, a little bit there. So, all right, we're talking about control hazards, and so let's just remind ourselves we've got the fetch, we've got the decode, we've got execute, write back, so on and so forth. Branches in our simple 5-stage pipeline are resolved in the execute stage. Okay, we're assuming an assume not taken path. I'm going to go ahead and throw a store word in here, and then let's just say this is a or instruction. So I'm going to go ahead and write the instruction stream here. We had a branch equal. Okay, we had a store word, and then the instruction that immediately followed the store word was an or. Okay, so that's the scenario we got. The branch is in the execute stage, and now it's going to be resolved. We are using the assume not taken path. Okay, and so what happens is if this branch resolves to taken, then we need to flush this instruction. We need to invalidate it because we incorrectly fetched it. Okay, and likewise, if you have a branch predictor, when it comes time to fetching that OR instruction, we would look to our branch predictor to figure out where we're going to fetch. Are we going to take the taken path or the not taken path? Right now, we just assume the not taken path, but if you have a branch predictor, you might actually assume the taken path if the branch predictor says so. Well, regardless, when you get to the execute stage, you compare what the branch resolved to where the branch or where you predicted it would go to. If your prediction was wrong, then you flush that instruction. So now the question is, well, how do we flush it? Well, just like we did before, we would essentially take the control signals that are being latched into this register, into this IFID register here, okay, and we would just set them to 0. That's it. That's it. Okay. Again, we leave the data alone. You know, half of we have a microarchitecture split into control and data, so part of our pipeline registers, each of our pipeline registers has control information, and then part of it has data information. We just leave the data information alone. That'll propagate down the pipeline. Yeah, maybe it'll burn a little bit of extra energy, but it's minor in the grand scheme of things. But then what we do is we just zero out the control part. Okay. So you zero out the control part, and now that OR instruction will have no effect. Okay. And just to remind you, we're going to, this is going to loop, let's say. And then let's say loop, at the loop label we have an AND instruction. Then let's fast forward over one cycle. Okay. So if we move on the next cycle, what will happen is the branch will move. Now remember, I want to remind you, this is supporting a branch delay slot. So the way we support the branch delay slot is we just don't flush this store word. That's it. That's it. It's as easy as that. Just don't flush the store word, regardless of the outcome of the branch. Just leave it alone. And then we flushed this guy. Okay, so I'm just going to call this a no op. Okay, and then now we're going to begin fetching the AND. Okay, and whoops, did something there that completely deleted a whole bunch of stuff. All right. And of course, then in this pipeline register, our zero control signals will propagate. Okay. Well, this is confusing. The zeros are actually, when the no op is in the decode stage, the zeros are actually stored in here. Okay. Okay. All right. So there we go. So all right. How do we support branch delay slot? Support branch delays easy. Simply don't flush the instruction that follows the branch. Okay. Okay. What if there is a branch or another control instruction in the branch delay slot? Well, just don't do it. Okay. The MIPS manual very specifically says non-deterministic results will happen if you do this. Don't do it. So do not put a control instruction in the delay slot. All right, so we need to take a little bit of time talking about what instruction could go in the delay slot. So you will have to do this for homework if you didn't already have to do that. And I've already alluded to previously what instruction you might pick. But what you want to do is you want to look at your basic block, and your basic block is here, right? You've got an entry into the basic block at this label. Okay, this label means that some other branch, whether it be the one down here or one elsewhere in your code, will cause you to enter this basic block. Okay, I'm going to just write this basic block. And then this branch marks the exit of the basic block. Okay, so the label is the beginning of the basic block, and the branch is the end of the basic block. Basic blocks are important. They're usually around 5 or 6 instructions. Let's count. 1, 2, 3, 4, 5, 6. Yep. And the larger the basic block, the more instruction level parallelism you actually have. And if you take my 538 class, we will talk a decent amount about basic blocks, and we'll talk about why they're important. And I'll discuss why larger basic blocks allow more instruction level parallelism. From the simple pipelining in order pipeline perspective, larger basic blocks means essentially fewer branch instructions. Okay, and branches throw us for a loop, pun intended, I guess. Okay. All right. So within this basic block, we want to look and see what instruction we can move into the delay slot. And so, first of all, it's an instruction that has to be executed unconditionally, whether the branch executes or not. Okay, and we also don't want to move an instruction that affects the branch. So here's an example. If we're drawing data dependencies, I'm going to draw this data dependency here. There's a data dependency here. This add I is producing T1, and then the branch is actually consuming T1. Now, T2 is used, is actually produced over here. So if we're continuing our diagram, we would say, oh yeah, there's another data dependency. That instruction is out of our basic block, so we're not even going to consider it anyway. Okay, none of these other instructions produce anything that the branch consumes. Let's just finish identifying data dependencies. We have the load word here, okay, and then this load word here, and then this OR-I, okay. Now, because we have this chain of data dependencies, starting with the first load word and going all the way to the final store word, we can't really move any one of these instructions down. If we move the load word down below the branch, it's going to affect program functionality. So the only instruction that we can really move, okay, down below the branch is this store word. Okay, so we can actually safely move it. It doesn't affect the branch, okay, and it's the last in the chain of dependencies, okay, that's required. Now, the only thing that's tricky about this moving this store word is it depends on T1, which T1 is getting modified here. So when we move it after, okay, if we move it after the add I, we actually need to modify this offset, okay? And that's the beautiful thing about that offset is we can modify it, okay, to then produce correct results. So how would we modify it? Well, let's look at what the add I is doing. It's taking T1 and it's adding 12 to it. Okay? So what we want to do is when we move the store word, we actually want to subtract 12 from the offset. Now remember, the offset can be positive or negative. So we can subtract 12, which we can have a negative offset. So we would have a -4 offset. Because then when the store word is executed after the add, okay, the add would add 12, but then the offset would add -4. When you add those two together, you get a +8 added to T1, and so then you would store T6 in the original location. Okay, so that's the thing. When you move instructions around, you have to make sure that you modify the instructions so that the program functions as it was originally designed. And oh, look at that. I have got a mistake in my code. Ha! Okay, that needs to be a -4. All right, I'll have to correct the slides. Okay. Yeah. Oh, speaking of slide corrections, okay, I've got two slide decks running in parallel, and this is what I'm struggling to figure out how to make this work. I have the modified one that has all of my gibberish comments written on it, and then I've got the original. And when if I find mistakes in the slides, then I lose the modifications that we made. So I'm still trying to navigate those waters. I wanted to go back because last lecture I talked about this this condition for forwarding, and I said that in lab you're going to actually we're going to merge the muxes rather than having two muxes like we showed in lecture. We're going to merge the muxes, which means we actually care about the use champ field. And so I wanted to point this out, that the first two conditions of your forwarding logic will look like this. The very first condition for RS is use champ. For RT, that would be use immediate. But for RS, it's use champ. So if use champ is asserted, then what we're going to set here is we're going to set the mux selection input such that it will pick from the shift amount field. And so we don't actually forward. Then the next condition is the very first forwarding condition, which is checking to see if there's a data dependency on the instruction immediately ahead of us. And then, of course, the the next else if would be checking the instruction 2 stages ahead of us. And then the final fallback condition will be go ahead and just grab the value from the register file. So if we're not using the immediate and we're not forwarding from the instruction immediately ahead of us and we're not forwarding from the instruction 2 stages ahead of us, then we must be reading it from the register file. Okay, I'm not actually going to save that because, well, I don't want to confuse this anymore. So anyway, all right. So I need to going back here when you move the store word to the other side of this and you actually have to correct the store word offset because it's using T1. And if you moved it like I did here without correcting the offset, then what you're actually going to do is you're going to store T6 into the wrong location. Okay, so all right, so see, I still produce errors in the slides, but all right. Now I put a blank sheet here. I don't know why. Okay, the store word in the previous example is a good candidate because it's executed regardless of the branch and does not affect the branch. Oh, I want to point something out. Maybe that's what I meant when I put in this this extra slide here. Let's see. So the compiler is going to do what it can to find a good candidate to move into the branch delay slot. And this snippet of code is actually one taken right out of our own crypto library. What it's actually doing is it's taking two values from two separate arrays and it's XORing them and then it's storing it into a third array. Okay, and it turns out XOR is what we refer to as a carryless add. It's a Galois field 2 add. Okay, and so in crypto land, this is a very fast add to do in hardware. And gosh, I'm almost I feel like going into a crypto abstract algebra lecture, but I'll spare you the details. Anyway, so it's very common to see code that's of this nature, and so what it means is that it's very common for the compiler to find something useful to put in this branch delay slot. Okay, but sometimes it can't find anything in the basic block before the branch. Okay, so what it will actually do is the very last resort is to put a no-op, but a no-op is wasted cycles, specifically one wasted cycle. So the compiler will actually look a little further reaching, okay, to find an instruction that can go in there. And so one thing it might do is it'll go and look at where the branch target is, okay, or it will or it'll look at the instruction that follows the branch. Okay, and so it will look at the two different paths that the branch might go. And if it can find an instruction in one of those paths, then it'll probably pick the path that it knows the branch is most likely to go to. Remember, the compiler is the one constructing code out of these branches and instructions, so it knows. Well, this is a loop, and in this case, it's a loop, so it's most likely to branch back to this load word, okay? Because it's a loop, and again, that follows that convention of backwards taken, forwards not taken, okay? So, so in this case, it might actually look and say, hey, can I actually put this load word in the branch delay slot? And so there's a couple of questions that the compiler will have to ask. Now, of course, when the branch is taken, then executing the load word, putting this load word in the branch delay slot would work just fine. But the question is, will anything be ruined? Will program correctness be hurt if the load word is executed when the branch is not taken. Okay. And what's interesting is the answer. Well, of course, it has to analyze the program, but the answer might actually be no, that it actually doesn't, because for this particular example, this code snippet is using T4. Okay. If the program doesn't care what T4 is after this branch exits out of this loop, then it can safely put that load word in the branch delay slot. Okay. So when it exits the loop, it will load some other value. The thing it has to make sure is that T1 plus 12 doesn't cause a problem. That's another thing. If you read from a location of memory that you don't have access to, that can cause harmful effects, and in fact can cause a seg fault. That's what a segmentation fault is. Cause an exception, which, by the way, is what we're going to talk about next. So anyway, it'll have to make sure that it can load. It has to make sure that the instruction that it puts in the delay slot, it has to make sure that if it's executed, even if the execution doesn't actually perform any work, it has to make sure that it doesn't cause any harm to the proper execution of the program. The store word is a perfect candidate because it has to be executed unconditionally of the branch, and the branch is not dependent on it. So you'll see store words very commonly in the branch delay slots. Okay. Okay, I already talked about this. Why is the add I not a good candidate? The answer, okay, well here's a quiz question. Why is the add I not a good candidate for being in the branch delay slot? So that's your third quiz question. Okay, all right, static branch prediction. Okay, we already talked about different static branch prediction techniques. The easiest one is just assume not taken. There's also backwards taken, forward not taken. That looks at the sign of the branch offset and determines based on that. And the other one, of course, is branch likely instructions, which allow the compiler to provide hints to the hardware as to which way it thinks the branch will most likely be taken. And then, of course, we have to add the recovery mechanism. So we've talked about the recovery mechanism. Okay? So those are the different static techniques, but the question is, can we do better? Now, keep in mind that MIPS was designed in the 80s when branch prediction really wasn't a thing. And so the branch likely instructions were the architect's way of coping with this. So static prediction. Backwards taken, forwards not taken is still a very common modern technique for small microprocessors, like your little ARM processors that go in your microcontroller embedded development boards. They use backwards taken, forwards not taken. And like your PIC32 probably uses some simple technique like that too. I should look at and see what the PIC32 uses. But remember, the PIC32 is a MIPS architecture, so it also supports the branch likely instructions. So if that architecture does not have a branch predictor, it would definitely behoove you to use those instructions. And the compiler and assembler generally take care of that for you. Let me see how we're doing on time. Oh, okay. I don't know where the time in this class goes. Well, I tell you what, I'm going to make this one a little bit longer. I know I've said I've been trying to keep things punctual, but we've got a lot of material to cover here. So think of this as a bonus round. Okay, you can pause it and go on with your life and then come back to the rest of this. But I'm already rolling, so. And they're probably not missing me at work. So let me at least, I want to at least cover branch prediction here, okay? Okay, so in the 90s there was a lot of research on dynamic branch prediction. And dynamic, in contrast with static, actually looks at the program as it goes along and keeps track of history. And so there's actually two types of history you can keep track of. One is local, which is what has this branch done the last few times it was executed, this specific branch that's being looked at. And then there's global, which looks at what were the, so many branch outcomes regardless of what branch it was. It could have been the same branch or other branches. I'll talk a little bit more about that. But okay, the simplest branch predictor is a 1-bit wide, okay, branch history table. Okay, so what you do is you got a table, and let's just for now assume it's infinite in size. So if it's infinite in size, or well, let's say it's 2 to the 30 in size, which is not infinite, but it's billions of entries. And what you do is you take you lob off the lower 2 bits of the program counter, because remember, for MIPS we enforce word alignment, so all the branches are going to be aligned, which means for every branch you encounter, the lower 2 bits of the program counter damn sure better be 0. So we take the rest of the bits, which actually have important information as to where the branch is located, and we feed that into a big old history table. Now I've got a slide whiteboard deck here. So this branch history table is filled with ones and zeros and so on and so forth, dot dot dot, all the way down, and we're feeding in PC, okay, 31 down to 2. Okay, that basically means, yeah, we're lobbing off the lower 2 bits. And I'm going to call this a branch history table, so BHT. And what we're going to do is we're just going to grab the last value out of that. So what this means is this history table is large enough such that every potential branch, okay, has its own entry in the branch history table. And if it was a branch, we just simply put a 1 if the last time it was executed was taken, or a 0 if it was not taken. So 1 for taken, 0 for not taken. Okay? Alright, so what we can do is, with our very simple predictor, is we're just going to say, hey, whatever it did the last time, let's just assume that's what it's going to do this time. Okay? So that works pretty well for loops, because if you can imagine, let's go back to our loop code and look at it. Let's erase all this. When we enter the loop, this works well for nested code, nested loops, and actually a lot of the things we do are nested loops. So, but it works well for non-nested loops as well. So when we enter this loop, we don't really know, based on what we're looking at here, what the branch did the last time it was executed. But if this is a nested loop, okay, and this loop had been executed previously, then we know that this branch, when it exited, it was going to be a not taken. Okay, so when we first enter this loop and we encounter this branch, okay, we're going to look at the history table, and it's going to have a 0 in the entry for this branch. So we're just going to say, you know what? We're going to assume it's going to do what it did the last time, which is not taken. So we're going to incorrectly predict this branch as not taken. So then we'll have to flush, okay, and then we'll come back up to the top of the loop. But see, now the branch resolved as taken. So our branch history table is modified now to have taken, so a 1. So when we come back and execute that branch for the second time, we're going to predict correctly. And we're going to keep doing that till we reach the end of the loop. When we reach the end of the loop, we're going to look at our branch history table, and it's going to have a 1 in it, and we're going to say, oh, well, we're going to predict this branch as taken. But because this is the exit of the loop, we're actually going to incorrectly predict, so it will actually resolve as not taken. So what this means is that for this simple 1-bit predictor, 1-bit wide history table, we will incorrectly predict twice for every branch loop. Now, if the branch loops 10 times, for example, well, that's an 80% accuracy, 80% correctness. Okay, 8 out of 10 times, if for 10 iterations, Okay, for 10 iterations, we will uh, we will predict correctly 8 times, incorrectly 2 times, so we have an 80% accuracy. Okay. All right. So, well, that's not too bad. Real quickly, before I leave this slide, I want to talk about aliasing. Right now, I mentioned, think of this as a 2 to the 30 entry table. Well, that's a lot of entries. So in real life, we don't put that many entries. In real life, we're probably looking at, and I'll have some graphs that show this, maybe 2 to the 10. So 1024 or 2048. Honestly, you can have very good results for our crypto machines. We actually only have a 32 entry branch history table. Okay, so only 32 entries as opposed to 2 to the 30, which is billions. And so if you don't have that many, so let's say we're actually only doing 2 to the 10 entries, then this is going to be what is it? 11 to 2. Is that right? 11 to 2 is 10. Yeah, that's so we take 10 bits of the program counter. We lob off the 2 lower significant bits of the program counter because those are always 0 for our branches because of word alignment. And then we take the next 10 bits and we feed of the program counter and feed into the branch history table. So because we don't have 2 to the 30 entries, we have a likely condition where 2 branches map to the same location in the table. So then they kind of fight each other. But remember, this is a prediction. It doesn't have to be correct. The more correct it is, the higher performance we get. The less correct it is, the lower performance, the less accurate we get of a prediction. And I've got some tables that show that later on. Okay, so that's what we refer to as branch aliasing. Okay, all right. So let's talk about this improvement right here. So right now, the problem with a 1-bit wide table is we're guaranteed to predict twice for every loop. Okay, can we improve that situation? And of course, the answer is yes. What we'd like to do is add what we call a little bit of hysteresis. Okay, now you all may have heard the term hysteresis if you study analog electronics, and it basically means like a comparator has hysteresis. When it changes, it then requires a more drastic change in the other direction to change its decision. So that's what we add here, is if we add 2 bits per predictor and have a little bit of a state machine, and I'm going to show that state diagram in a second here, then we can be a little more slow to changing our prediction, which means we can then actually only mispredict once per loop. Okay? And if we have 10 iterations per loop, then that means we up our accuracy, branch prediction accuracy from 80% to 90%. Okay, so how do we do this? Well, here's our state diagram. So with 2 bits, we have 4 states. Okay, with 1 bit, we have 2 states. It's either taken or not taken, and we base it off of what we did previously. With 4 states, or with 2 bits, we have 4 states now. And so what we have is up here we have what I call the strongly predicted the strongly taken state. So as the branch continues to resolve as taken, we basically just hang out here. Okay, and the prediction is going to be predict taken. Okay, when the branch is not taken, okay, then we transition over here to this state. And this is what I call the weakly taken state. Okay, and so in the weakly taken state, we're still going to predict taken. Okay, we're still going to predict taken. Okay, but we're kind of weakly taken. All right. Then if we get another not taken, well, now we change our prediction. Okay, and we predict not taken, and this is our weakly not taken. And then if we get not taken again, then we transition to strongly not taken. Okay, so 4 transitions are 1, 2, 3. 3 not takens gets us from the strongly taken to the strongly not taken. Okay. Now, in the case of our loop, okay, when we're in the process of executing the loop, okay, we're going to be the branch, if it's at the bottom of the loop, is going to continually be taken. So we enter the loop. Okay, when we enter the loop, all our branches are going to resolve as taken, taken, taken. And each time we're going to predict taken. When we exit the loop, we're going to encounter a not taken situation. And that's going to move us to the weakly taken. But now, when we come back and execute that loop again, and again I'm saying we're assuming a nested loop. When we come back and execute that loop again, we're going to predict taken. Okay? So when we execute the branch again, when we start the loop, we're going to predict correctly. So now and then of course when we're in the middle of the loop, as soon as we get the first taken, we go back to strongly taken. So what it means is that with this particular 2-bit predictor, we are actually going to predict correctly 9 out of 10 times for a loop iteration of 10. Okay, so in other words, we're going to mispredict only once for every loop execution. So again, I call this, we add a little bit of hysteresis because it now takes 2 mispredictions to change our prediction. Okay, and the same goes for the not taken path. You can see. Now, of course, what do you assign these in terms of state values? You can just go sequentially like this, however you want. You know, it really doesn't matter. So then in the table, you're strongly, well, actually, here let's match a little bit, match the single predictor a little. We'll call taken 1 1, and the strongly taken is 1 1, and the strongly not taken is 0 0, and then these are our points in between. Okay. So what will happen is now in the table, okay, in your table over here, we're going to go ahead and we're going to increase. Let's see. We're going to increase the size of this table to accommodate, okay, more bits. Okay, there you go. So now that's a 2-bit predictor. So we've doubled the amount of state that we have to hold, but I mean, if it's 1024 bits or 32 entries like in our simple processor, okay, it's not a lot of extra state. Okay, each one of these each bit's going to consume a flip-flop in our table, or if it's large enough, we'll use an SRAM to actually store this prediction table. Okay? So that is your simple 2-bit predictor, and this is often called a loop predictor because it predicts loop branches very well. Okay. Okay. And so again, the accuracy of this 2-bit predictor can be well, it's 90% if our loop iterates 10 times. And the beautiful thing about crypto code is a lot of times we're looping 12 to 20 times. Okay? Because if we go back to this snippet of code that I have here, this array is an array of 32-bit elements, and in crypto, especially elliptic curve crypto, you're actually working on very large integers that are maybe 384 to 512 bits in length. So you're working on these large integers, and what you do is you take them and you chunk them up into 32-bit words. And so each iteration of your loop is going to operate on that single chunk of code. If you're doing multimedia or whatever, each word might be a digital sample of audio, for example, and so if you've got lots of audio, you're looping a lot. So these predictors are very accurate with loopy code. Okay. I wanted to continue, but man, I'm just going to overload you with information here. So I think we're at a safe stopping point. And so let's see. What do I? I want to throw another quiz question in here. Okay. Okay. I want you to define. I want you to. What do I mean by branch aliasing? What did I mean by branch aliasing? So this might require you to back things up a little bit here, but define the term branch aliasing. Okay. And so we're going to stop here, and then we'll pick up next time. What we're going to talk about next time is how to improve upon the loop predictor. And the loop predictor uses purely local information, and the spoiler alert is that to improve upon our predictor, we need to incorporate global history as well. And then I'm gonna show you some graphs that talk about accuracy, and I'll talk about a couple more advanced branch predictors that are used in 90s processors. Modern branch predictors use machine learning techniques. They're very advanced. If you take my 538 class, we'll spend a lot more time on branch prediction. Anyway, I hope you all have a good day, and I hope you're enjoying these lectures, or at least maybe not hating them. Okay.